let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 391, Differential Equations. We are going to learn to solve more differential equations, obviously. We are currently dealing with second order linear differential equations. And we are going to continue with that. So the main plan for today is to talk about the behavior of solutions for second order linear differential equations, and also, I guess at the same time, for higher order differential equations. We're going to also talk about the idea of a particular solution, and we're going to look at one method of finding a particular solution that we call variation of parameters. The other one we'll deal with tomorrow. So particular solutions would apply to what we call non-homogeneous differential equations, and we're going to deal with that today as well. So we're going to introduce a new concept, the non-homogeneous differential equation. Basically, if we don't have a zero on the right side, how do we solve things? I'm going to show you how to solve things. It's going to involve something called a particular solution, and I'm going to show you one method for finding such a solution. So let's actually jump into that. And let's turn off the cameras because it's a little buggy when the cameras go. Okay, so this is actually something that we covered last time. So this is just a recap right here. Just want to remind you, we started talking about second order linear ODEs. We call this SOLDEs. And I'm pretty much jumping around between 3.1, 3.2, and 3.3. For today's class, I'm going to be jumping around 3.5, but ultimately we're going to come back to doing that as well. And then we're going to do 3.6. So we introduced the idea of what a second order linear differential equation is. It's just a guy that looks like this. When the right side is zero, we call that a homogeneous second order linear differential equation. And we saw how to solve those. Pretty much, you assume a solution looks like y equals e to the RT. This yields a characteristic equation. This becomes a quadratic for a second order linear differential equation. But in general, it will be an nth degree polynomial for an nth order linear equation. However, for the second order linear equation, we have three cases based on how many solutions we have. So if we have two distinct real solutions, our general solution for the homogeneous version is going to look like this. If we have one solution to the quadratic, we have a repeated root scenario, as it's called. Our solution would look like this. And we actually covered 3.4, which talks about reduction of order and repeated roots. And we actually derived why it ends up being a t times the other solution. And it's always going to be that. So 3.4 is where we looked at a general method called reduction of order that explained why we multiplied by the t here. But once you know that you're looking at a second order linear differential equation, you automatically know in this scenario, once you find one of the answers, just multiply that answer by a t, and that will give you the second answer. If we have complex roots, it breaks up into sines and cosines and exponentials, which follows directly by Euler's equation. E to the I theta equals cosine theta plus I sine theta. We did a few examples of solving those, and that ended that section. And yeah, again, we moved on to 3.4, where I proved why we had to multiply by t to get the second solution. And I also showed that this reduction of order method is actually something that works in general. So here, where was it? Here in this scenario, we had a second order linear differential equation, but it did not have constant coefficients, as we were assuming in the last section, but reduction of order still actually worked out to help us find a solution once we have one. So reduction of order is a good method in general. It helps us find a second solution if we already know one solution, and it allows us to know that whenever we had a repeated root, multiplying that by t gives us another solution. Okay, now I want to talk about some facts about the solutions, right? So as you might have noticed, I assume that once we make a certain assumption in this box, that there are three possibilities for the solution. And you'll notice that all of them have two parts to them. there's a C1 times one function plus a C2 times a second function. Notice that there is no C3 times a third function, or C4 times another function, or notice that there isn't just a C1 e to the RT. When we had a repeated root, you might have been tempted to just say, oh, it's just one answer, so it's C1 e to the RT, but this would actually be incorrect. You would actually have missed a part of the solution. There is a theorem that would tell us that a second order linear differential equation should have two distinct solutions. There should be a y1 and a y2, such that when I do c1 y1 plus c2 y2, I get the general solution to this differential equation. And that same theorem would also tell us that there will not be a third kind of solution or a fourth kind of solution. There will be exactly two kinds of solutions for a second order linear differential equation. And facts like that about solutions is what I want to explore now. Given some nth order linear differential equation, how many solutions should you be able to find? What form would a solution look like? How do we know what we're actually chasing, et cetera, et cetera. So that is what we're going to cover right now. It's going to be a lot of theory today. A lot of it is going to have to do with linear algebra, but a lot of the theory, believe it or not, I will put off until after our test on Friday. Which, by the way, as you guys all know, we do have a test on Friday, but I don't have any new information to share with you about that. So let's just move on. So a higher order linear differential equation is just an equation that looks like this, right? So it's y to the nth derivative plus some function times y to the n minus first derivative, counting all the way down to some function times y equals 0. This is a homogeneous higher order differential equation, right? So we really want to focus on the second order guys. However, I'm going to talk about the nth order guys. I'll talk about some things that work in general for the nth order guys, and then I will actually tell you what this means for the second order guys as well. So that when we get to chapter 4, we can get through the theory a lot easier. So let's actually get through to that. I don't know why it does that. Okay, let me not click on that. It seems to shift things. Okay, so whenever we have 0 on the right side of a linear differential equation, we call that homogeneous. And so the solution to such an equation is called a homogeneous solution or a complementary solution. And our notation for this is going to be y sub h or y sub c. I'll tend to use y sub h out of habit, but if you read from certain sources, they might also use y sub c for complementary, and h is for homogeneous. They refer to the same thing. So whenever I write y sub h from this point onwards, I will be talking about the homogeneous solution to a linear ODE. Okay. Now, note that if I say, for example, y1 is a solution to this differential equation, what it actually means is if I take y1 and I find all its derivatives and I plug into this equation becomes true, which means p times y1 prime plus q times y1 prime, p times y1 double prime plus q times y1 prime plus r times y1 will give us 0. Okay, so here's a differential equation that I care about, second order linear differential equation. To say that a function is a solution of that means that if I plug that function into this equation, the equation will hold. Here's an important fact about a solution to a differential equation. If you know one solution, if y1 is a solution to a differential equation and c is any constant, then a constant times that function is also going to be a solution automatically. In the box, what this means, the fact that you want to remember is a constant times a solution is a solution. So when you're looking at a differential equation, you should know that automatically. If I find a solution, then a constant times that is automatically a solution. We saw this in lecture, the very first lecture, when we were looking at the equation y prime equals y. And we saw that, you know what, y equals e to the x is a solution here. But we could also say, well, a constant times e to the x is also going to be a solution. This is something that we can actually say in general. And here is how we know that we can say that in general. So if y1 is a solution, then consider y equals c times y1. This means if I plug it into my differential equation, I would have p of t times cy1 double prime plus q of t times cy1 prime plus r of t, I think is the notation I was using up here. Yeah. R of t times cy1. That is going to be equal to, well, it's a derivative. A derivative of a constant times a function is just a constant times the derivative of the function. So I can actually factor out a c, and I would have py1 double prime. Here I can factor out a c. I would have qy1 prime. In the last one, I can factor out a c. I would have c times that. That is, of course, equal to, where is this? This is, of course, equal to, well, c is a common factor. I can factor it all out. And by the assumption, since y1 is a solution to the homogeneous equation, I know that this equation holds true, which means that this whole part here is actually 0. And so this entire equation is 0. And so notice that if I plug in cy1 for my function, it ends up giving me 0, which is what the equation says I should have gotten. So that means that cy1 is also a solution. So every time you find one solution, a constant times that solution is automatically a solution. So if someone comes to me and say, oh, I found a solution to this differential equation, e to the x solves this differential equation. And then someone else comes to me and says, oh, I found a solution to this differential equation. 7 times e to the x solves the equation. Then in fact, these two people have given me no new information. They're both saying exactly the same thing. If e to the x is a solution, then yes, automatically 7e to the x is a solution, or 5e to the x is a solution, or 3.1e to the x is automatically a solution. A constant times a solution is automatically a solution. Hopefully you can see that this will generalize to higher order as well. There's nothing special here about having a second derivative. If I had the nth derivative, I'd be able to factor out constants and do exactly the same thing. So this will actually generalize very naturally to higher order linear ODEs as well. In general, if you have a solution to a linear ODE, no matter what order it is, a constant times that solution will also be a solution. So that is a very important fact. Once you have a solution, anyone multiplies it by a constant, they give you no new information. A constant times a solution is automatically a solution. Here's another fact. If I have two solutions, y1 and y2, and c1 and c2 are any two constants, doesn't matter what they are, then this expression c1y1 plus c2y2 is also a solution. This expression here is called a linear combination of y1 and y2. So if you have a bunch of things, you multiply them all by a constant and add them together, that sum, that expression that you get, it's called a linear combination of the things. And basically, this fact states that any linear combination of solutions is a solution. So if someone comes and they say to me, hey, here's a differential equation, e to the x is a solution, and e to the 2x is a solution, then it automatically means that c1 e to the x plus c2 e to the 2x is a solution, right? And if you look back at what we did last class, this should start to make a little bit more sense. We pretended our solution was e to the rt, but then I found two r's. There's an e to the r1 and an e to the r2t that solve the solution. Automatically what it means is that the linear combination is going to solve the solution, right? That is the fact that I'm mentioning here. A linear combination of solutions is automatically a solution. This fact is called the superposition principle, if you wanted to look this up a little bit more, but you don't really need to know any more than that. And here you can see why, if we set y equals c1 y1 plus c2 y2, then our ODE would become Well, P times C1y1 plus C2y2 double prime plus Q times C1y1 plus C2y2 prime plus R times C1y1 plus C2y2. That will give us, so here I'm plugging into the left side of ODE. And then to simplify, again, derivatives distribute across sums and you can factor constants out. So you'll notice what I will be able to do is I'll be able to group all the guys that are attached to C1, and then I can factor out the C1. So I end up having C1 times P(y1) double prime plus Q(y1) prime plus R(y1), and then I'd be able to factor out a C2 from the other set. So this is y2 double prime plus Q times y2 prime plus R times y2. And again, since y1 and y2 are homogeneous solutions, these two parts here would go to 0, which of course means the entire thing is equal to 0. And so C1y1 plus C2y2 is a solution if y1 and y2 are. So if I have two solutions to an ODE, then any linear combination of those two solutions will also be a solution. Okay. Now again, hopefully you see that the above generalizes naturally to higher order linear differential equations. There's nothing special about having the second derivative here. If I had three derivatives, it would be the same thing. The derivative distribute across sums and I can factor constants out. So I'll be able to group guys based on the C1, C2, C3 or whatever. And then I can find that what's inside the parentheses will go to 0 by assumption. And so we get a solution. Okay. Now, here is something that is obviously a concern based on what I said above. It means then, if someone tells me a function is a solution, then if someone else tells me a constant times that function is a solution, well, it's kind of redundant. And if I know that two things are a solution and then someone tells me, well, C1 times this one plus C2 times that one is a solution, again, it's a redundant thing, right? Knowing these two solutions, I automatically know there's a constant times it, times the function is a solution, and I automatically know linear combinations of solutions are solutions. So for anyone to give me solutions of that form, they're going to be redundant. And so now we have to worry about, well, redundancy of solutions. So if I'm working on some big important differential equation, I know I have a few solutions, but I need to find other ones. How do I know that the guys that I'm finding aren't redundant? How do I know that they don't already have to deal with the solutions I've already found? That's what we're going to look at, right? So like I said, if we pretend that e to the t was a solution and someone told me that 5e to the t is a solution, they didn't give me any new information. These two, telling me both of these pieces of information is actually redundant, right? So how do we actually get rid of redundant solutions, right? And I'm actually going to show you guys how you would actually do that. It requires us talking about something, a definition that is called linear independence. Okay, so and again, we're focusing on soldes here, but it's going to generalize very naturally to higher order differential equation. Suppose y1 and y2 are two known functions. They are said to be linearly independent if the only solution to this equation, c1y1 plus c2y2 equals 0, is the solution c1 equals 0 and c2 equals 0, right? So if I set up a linear combination of a bunch of guys and set that equal to 0, if the only way to get that equation to work out is to choose all the coefficients equal 0, I say that the functions are linearly independent. If I can find non-zero solutions for the coefficients, they're called linearly dependent, right? Now, that might seem like it comes out of left field. Like, what does that definition even mean? Here's what it actually means. The above actually means that neither function is going to be a constant times the other, and so these two functions are not redundant. How do I know? Well, let me show you how do we know. How do we know that that definition, if that definition holds, I don't have redundant solutions? Well, suppose we can find a non-zero C1 or C2 that solve the equation C1y1 plus C2y2 equals 0. And suppose, for the sake of argument, and it'll work the other way, suppose without loss of generality, that's just a term that just means you can, if we pretended the other one was not 0, we get the same thing, that our C1 is not equal to 0. This means I would actually be able to solve for the y1, and my y1 would be written as C2 divided by C1 over y2. In other words, this would mean your y1 is a constant times y2. So the thing is, if we can find a non-zero solution, it necessarily means that one of these functions is a constant times the other function. And that makes it redundant. So in order to avoid redundancy, this is a quick check that I could do. I can set up this equation and try to find the solutions in C1 and C2 of that equation. If the only solution is all the C's are 0, then I know that these two functions are not redundant. They are what we call linearly independent. They are distinct, they're different. It's not a constant times another one. Now, this definition does generalize very naturally. So let's say I have n solutions, or n functions, y1, y2, all the way up to yn. I call them linearly independent if I set up a general linear combination, set it equal to 0. If I set up a 0 combination, then the only solution is all of the coefficients must be 0. If that is the case, I call all these functions, y1, y2, up to yn, linearly independent. If I can find non-zero solutions, it will mean that they are dependent. And the implications are the same. Essentially, you are guaranteed, if you find that all of these guys are equal to 0, it is a guarantee that none of these functions can be written as a linear combination of the other functions, meaning that none of them are redundant. They're all very important for us to state in the answer. Okay, so here's an example. E to the t and 5e to the t are not linearly independent. Well, how would I show that? Well, if I can set up C1 y1 plus C2 y2 equals 0, where let me call my y1 e to the t, and let me call my y2 5e to the t. So what I have here is C1 e to the t plus C2 5e to the t equals 0. Now here's a solution. Note, C1 equals -5 and C2 equals 1 is a solution, right? Since if I take 5 times e to the t, -5 times e to the t, plus 1 times 5e to the t, I get 0. What that means, I just found a non-zero solution to this equation. This means e to the t and 5e to the t are not linearly independent. In other words, as far as differential equations are concerned, these two guys are redundant. If you tell me one of these, you might as well tell me the other one. There's no need to tell me both of these guys are solutions. It's redundant. one is a constant times the other, right? Now, obviously, we can eyeball this and see that one is a constant times the other. 5e to the t is just 5 times e to the t, right? But it's not always going to be obvious when this kind of redundancy is happening, especially when you have more than 2 functions. But I thought I would just illustrate with showing you that 2 functions are not linearly independent. However, let's look at this one, e to the t and e to the 2t. It turns out that these are linearly independent. In fact, this is going to be a general thing that you can assume from now on. If you have an exponential and the powers are different, right? The powers are different functions, then those 2 exponentials are linearly independent. So e to the t is going to be different from e to anything else t. And so let's just actually illustrate this with e to the t plus e to the 2t. So set up the equation. Set up c1 e to the t plus c2 e to the 2t equals 0. I claim the only solution is c1 equals c2 equals 0. Assume to the contrary, it's not. Right? If someone says, I don't believe you, I think I can find non-zero solutions to this equation. Assume to the contrary, there are non-zero solutions. Right? So I say, you know what, c1 equals c2 equals 0 are the only solutions. And someone says, I don't believe you, I think we can find non-zero solutions. And I'm like, okay, go ahead, find them. Then if we assume, I can do this by cases just to make it a little bit clearer. Case 1, I can have c1 equals 0, but c2 is not 0. Or case 2, I can have c2 equals 0, but c1 is not 0. Or case 3, I can have c1 is not 0 and c2 is not 0. Now, case 1 and case 2 are very similar, right? Now, case 1 and case 2 are similar. So suppose we're in case 1, and the idea will be the same for case 2. So here I have c is 0, but c2 is not 0. This means 0 times e to the t plus c2 e to the 2t would be equal to 0. Well, this means that c2 e to the 2t equals 0. But what would that mean? Well, that means that your c2 has to be 0. I have a constant times an exponential equals 0. The exponential is never going to be 0, so the constant must be 0. And so, I get a contradiction. Both must be 0. Now I can jump to case 3. What if someone tells me, you know what? If one is 0, then yeah, it can't work. But what if both are not 0? So then I would have c1 e to the t plus c2 e to the 2t equals 0, but c1 is not 0 and c2 is not 0. Here's something that I could do though. I could divide through by e to the t because it's an exponential. And then notice now I can solve for e to the t. E to the t is going to be minus c1 divided by c2, which is a constant. Now, of course, lightning strikes, that doesn't make any sense. It's e to the t. E to the t is not a constant. If I pretend that there are non-zero solutions for both of them, I would end up with the conclusion that the exponential function is a constant function. That doesn't make any sense. So we end up again with both must be 0. So if I have two functions, e to the t and e to the 2t, and I set up this equation, the only solution for that in C1 and C2 is that both C1 and C2 must be 0. What does that mean? It means that neither of these guys are redundant in the sense of being solutions to a differential equation. If you tell me one, it would be very important for me to find the other one. I can't get away with thinking that one of these guys is redundant. They're not redundant. They are what we call linearly independent. And whenever we have linearly independent solutions to a differential equation, it means that none of those solutions are redundant. We need all of them. So that's going to be a very important fact. Now, what I did, I warned someone else that we're going to do a lot of linear algebra today. I warned someone else that we were going to do, I was looking at a comment, but they basically said what I said. I warned someone we're going to do a lot of linear algebra today, and that's what we're going to jump into now. So here, you guys could probably follow this, but again, it's because I have very specific functions here, exponentials. Someone can say, well, yeah, I guess it will work out for exponentials, but it wouldn't work out for other stuff. And so what if we had some weird functions right here? How do I know that something like this would work out? It's very hard to know in general that something like this is always going to be true, unless you think of linear algebra. Linear algebra is going to make it easy, quote unquote, to figure out that this kind of thing would work in general, even if we're not necessarily talking about exponential functions or very nice functions. So just a quick recap from linear algebra. This thing is an n by n linear system. It's n by n because notice it has n equations and n unknowns. The a's are constants. My x1, x2, x3, all the way up to xn are the variables. And these guys over here are constants. So, you know, example, like if I have 5x plus 3y minus 2z equals 4, and 2x minus z equals 7, and x plus y minus 2z equals 9. This is what we call a 3 by 3 linear system. Okay, so that's called a linear system. Now, this here is an n by n. It's called a square linear system. Now, in general, you don't have to be square, but the square ones are the ones that we are going to care about, and I'll show you why in a bit. Because we are always going to be able to build things up to a square system, and it's going to allow us to use some nice theory from linear algebra. Okay. So like I mentioned here, the a's are constant, the x's are the variables. The system does not have to be square, but we only care about the square ones. I can write this in matrix form in this way. If you remember how matrix multiplication works, you'll realize that this equation here is exactly equivalent to writing out a list of n equations there. So this is called a matrix form. This can be written in this form, ax equals b. So someone can call this guy a, they can call this guy x, they can call this guy b. And then that leads to this version. And this representation is called a matrix representation of a system. The A is called the coefficient matrix because it has all the coefficients in it. The X is called the solution matrix because, of course, if you want to find the solution to this system of equations, you're really finding all the X's, the X1s, X2s, all the way to Xn's. So that's called the solution matrix. And this guy over here is called the constant matrix because it just holds a bunch of constants in it, right? So for example, this one right here could be written as 5, 3, minus 2, 2, 0, minus 1, 1, 1, minus 2, times x, y, z equals 4, 7, 9. I could write this linear system in matrix form like that. And then the big matrix in the front is the coefficient matrix, the x, y, z is the solution matrix, and the 4, 7, 9 is called the constant matrix. Okay. Now, here's the thing about square matrices, which is why it's very nice. There's a thing called a determinant, and I'm not going to define for you what a determinant is. I'm going to assume you know how to find them because you would have definitely done them. At minimum, you would have done these guys in Calc 3. So you should know what a determinant is and how to compute them. So, and I asked you guys to review linear algebra, so I'm not going to go over that. So if D is the determinant of A, right, which is the coefficient matrix, and if I call AI to be the matrix we get, if we take A and replace the ith column with B, right? So for example, to use this same guy as an example, A2 would be the matrix I get if I replace the second column by the guy that's over here, 4, 7, 9. And then I leave everyone else the same. So I take the constant matrix and I put it as a column in the matrix. This guy is what I would define as A2. Now, D sub I is the determinant of that. So I would also say something like D2 is just the determinant of A2. Okay, so I'm just introducing notation to be able to state a very important theorem called Cramer's rule. Very important theorem. If I have a square system of linear equations, Cramer's rule can tell us about solutions to that system. You just use this formula in electrical circuits? Yeah, great. Linear algebra is actually pretty applicable. You can apply it to various areas of math. You can apply it to various areas of computer science, engineering, all over STEM. It's really amazing. Linear algebra is actually more applicable than calculus itself, which is crazy when you think about it. So yeah, so I do expect you guys to have seen everything I'm talking about at some other point in time, which is why I'm really talking very fast right now, because I do expect you guys to be able to follow along relatively well. Cramer's rule. If you have a square system, it does not work for non-square systems, because you should remember that we cannot take determinants of non-square matrices. If the determinant of A is not 0, then it turns out the system will have a unique solution. And we know what the solution is going to be given by. It's going to, each xi is going to be given by di divided by d. So my x1 is going to be d1 divided by d. My x2 is going to be d2 divided by d. My x3 is going to be d3 divided by d, etc. Where the d's are defined like I showed you up here, right? So if our determinant of the coefficient matrix is not 0, we will have a unique solution. And I know exactly how to find that solution, in fact. If your d is equal to 0 and one of the di's are not 0, then the solution is inconsistent. The system is inconsistent, meaning it has no solution. There is no vector x that will solve it. If my d is 0 and all the other di's are also 0, then what that results in is that the system is dependent. Dependent basically means there are an infinite number of solutions. There will be an infinite number of vectors x, right? There'll be an infinite number of sets of x1s through xn's that will solve this system. And Cramer's rule tells you about all these scenarios. And by the way, another thing you guys would remember from linear algebra is these 3 scenarios is all the possible scenarios that could ever exist for a linear system. A linear system, there is not going to be any other scenario. A linear system of equations that's square, well, in general, it's either going to have a unique solution, or it's going to have infinitely many solutions, or it's going to have no solution. There is no other possibility. Cramer's rule tells us about each of these possibilities based on this. Okay, and again, I expect you guys to know about this, so I'm going to rush through an example very quickly, because even later on after the test, when I'm doing theory, I'm going to be doing a lot of this. So I want you guys to be able to see what we're talking about. So here's a system of equations, x plus y equals 3 and x minus y equals -1. I'm going to solve this using Cramer's rule. First thing I would notice is that this is 1, 1, 1 minus 1 times xy 3 minus 1. And this means that my d is going to be the determinant 1, 1, 1 minus 1. That is going to be -1 minus 1 equals -2. My d1, or in this case, just to be suggestive, I can call it d sub x. This means I go to d and I replace the x column. So this is the x column and the y column. I replace the x column with the constant matrix. So replace that with 3, 1, 3 minus 1. Leave everything else the same. I would get -3 plus 1. This gives us -2. My dy is going to be look at D, but replace the Y column with that. That's going to give me -1, -3. That's going to give me -4. So that is all the notations that I have here. I'm going to take the constant matrix and I'm going to replace the X column, find the determinant, that is called D sub X. If I replace the Y column, find the determinant, that is called D sub Y. Now, Cramer's rule says, by Cramer's rule, my X is going to be dx divided by D. That is going to be -2 divided by -2 equals 1. And my Y is going to be dy divided by D. That is going to be -4 divided by -2 is 2. And so this means that X comma Y equals, so this is what I would call my vector X. So my vector X in the notation above is, in this case, looks like X comma Y, and that's going to be equal to 1 comma 2. And you can check this. This is actually the solution. You can check this. This is the answer. In fact, this is the answer. Emphasis on the. If you were to sketch both of these guys in an equation, you'll notice that they intersect in one point, namely the point 1 comma 2. If you were to draw these graphs, X plus Y equals 3. So you would have a graph that looks like this. That would be the graph for the first line. And then you'd have another graph looks like that. Like that. That would be a graph for the second line. And you'll notice that the point where they meet will be the coordinate 1 comma 2. That's very small. This shouldn't go through the origin. Not through origin, but I don't want to redraw it. Right, so that is using Cramer's rule. I can actually use determinants to solve this system very quickly. So that's called Cramer's rule. So I just showed you a 2 by 2 case. However, no matter how big this system is, it could be a 3 by 3, a 4 by 4, a 1000 by 1000. It does not matter. This process, provided that D is non-zero, can find the unique solution to that system. If this D was 0, then it turns out there is no unique solution. I will either have no solution or infinitely many. But here, the emphasis is going to be on unique solution because I want a unique solution. I want to talk about the only solution to something. So definitely uniqueness is going to be the emphasis here. Corollary, if B equals 0, right? So this means that I have AX equals 0, then you know that X equals 0 is obviously a solution. A times the 0 vector is going to be the 0 vector. And if D is not 0, then it is the only solution. And that follows automatically by Cramer's rule. So how do we apply this to what we were talking about before, to figuring out when functions are not redundant in some sense? Well, start out by writing down the equation that we care about solving. C1y1 plus C2y2 plus C and dot, 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 plus C and yn equals 0. If the only possible solution is this, all of them equal 0, then they're linearly independent. And there is a unique solution for the CI. That's what it would mean. So essentially, what we want to be able to do is we want to show what that solution would have to be. I can take this equation and I can keep differentiating it, and I can get an equation where they're all derivatives, then all second derivatives, and so on and so forth. And then, oh, I think there's a, give me a second. There's a delivery guy at the door. Hold on a second. Okay, I'm back. Let me sanitize up here because you know we're in a pandemic. Okay, so where were we? I can repeatedly differentiate this, but I'm careful to just differentiate it n minus 1 times. That way, I have a square system of equations. I will have n equations and n unknowns if I just decide to stop differentiating after n minus 1 times. Now, in this case, remember, my y1, my y2, and etc., those guys are actually known. In this situation, my C1, C2, all the way up to Cn, those are the guys I don't know. So technically, the C1, C2, blah, 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 those are the x's. Essentially, this system can be written in matrix form to look like this, where I have this matrix here, where I have all my functions and their successive derivatives going down the rows. I would have C1s all the way through Cn's in this column here, and then I have all zeros on this side here. So we get a system where the A, the coefficient matrix, is this, the X is this, which is the guy that we want to solve for, and the B is this, which is just the zero vector. Now, of course, C1, C2 to Cn equals the zero vector is a solution, right? If I plug in zeros for all the C's, then matrix multiplication is going to get me that this equation holds. So that's a solution. That's easy to see, right? This matrix times the zero vector gives me the zero vector. That is fine. Now, to guarantee that it is the only solution, which is what we want for linear independence, Cramer's rule tells us what we need is that this determinant here should not be zero. So in other words, as long as I can make sure that this determinant is not zero, then it's the same as saying all these functions right here are linearly independent, in the sense that they're not going to be redundant when I'm using them to solve a differential equation. If they're each are solutions individually to a differential equation, then each of them individually is important for us to worry about. None of them are redundant, none of them should be thrown away. So I have a bunch of solutions, a bunch of functions here, take their derivatives n minus 1 times to get new rows. If the determinant of that is not zero, we have linear independence. So Cramer's rule from linear algebra gives us that. Now, whenever I have a set of functions where none of them are redundant, I call that a fundamental set of solutions. Okay, so in this case, if this determinant is not zero, then the functions y1, comma y2, comma y3, all the way up to yn, I call that set of solutions a fundamental set of solutions. It means that they would solve at some nth order differential equation, and they solve it in such a way that none of them are redundant. I actually need all of them to describe the solution to this differential equation. Now, obviously, this determinant is pretty important. So what do we do when something is important? We give it a name. The determinant above is called the Wronskian, right? So there's something that's called a Wronskian. That's what you should now know. That's the new word of the day, Wronskian. The Wronskian is a determinant, right? It's called, you think of it as a function. It's the Wronskian of the functions y1 through yn. It's just this specific determinant here. Now, sometimes we leave off this and just write w when it's understood what functions we're talking about, but that actually is the determinant. This is called the Wronskian, and as long as it's not zero, we can know that none of all our solutions, all the functions here, are a fundamental set of solutions. So how do I know if a set of functions are linearly independent? Well, find their Wronskian. If the Wronskian is not zero, then they're linearly independent. And if the Wronskian is zero, then they're not, right? And that's just it. And so that leads to a third very important fact. The functions y1 through yn are a fundamental set of solutions to an nth order linear ODE, if and only if the Wronskian of them is not zero. And of course, this assumes our functions are continuous and whatever, right? If our functions are discontinuous, then everything I say, all bets are off, doesn't work. But yeah, so that leads us to a very important fact. Here's what the Wronskian would look like for equation 1. So equation 1, if I scroll back up here, equation 1 is this ODE that I'm talking about here. well, it's this. I labeled it somewhere, but I forgot. This is equation 1. I labeled it equation 1 somewhere, but I forgot where. So here's what the Wronskian would look like for a Solde. So equation 1 here, I'm referring to py double prime plus qy prime plus ry equals 0. Now, if y1 and y2 are solutions, then the Wronskian of those solutions would be the determinant y1, y1 prime, y2, y2 prime. So this would just look like y1 times y2 prime minus y2 times y1 prime. So this guy here is called the Wronskian of two functions. All right, so that's how you'd compute it. It's actually that expression, but you can think of it as a determinant. And of course, for three functions, and this should be clear, but I'll just write it down. For three functions, let's say y1, y2, y3, the Wronskian is just going to be the matrix y1, y2, y3, y1 prime, y2 prime, y3 prime, y1 double prime, y2 double prime, y3 double prime. And you stop at the double prime because you want it to be a square matrix. You want a 3 by 3 matrix. And you do this for all orders. So if you have 4 functions, you just take derivatives 3 times to get a 4 by 4 and so on. You can actually construct a Wronskian by this construction that I mentioned here. Okay, now what we're going to do is I'm going to want to look back at our original examples and show using the Wronskian whether they're not linearly independent or not. So earlier we saw that e to the t and 5e to the t are not linearly independent. And we saw that e to the t and e to the 2t are. How can I do that in a very quick way? How can I show that they're linearly independent or not easier? So here, let me show you. E to the t and 5e to the t are not linearly independent. How do I know? Well, if I find the Wronskian, that would look like e to the t, the derivative of that would be e to the t. I can have 5e to the t, the derivative of that is going to be 5e to the t. This will give me 5e to the 2t minus 5e to the 2t. Gives me 0. Bad. Well, I shouldn't say bad. It's not morally bad or anything. It's just bad in the sense that it's not linearly independent. Okay, the Wronskian has to not be 0. But notice here, this is something that we knew would happen, but it's nice to just get a confirmation like this. And for general functions that are not exponentials, this thing would still work out. If they're not linearly independent, the Wronskian is going to give you 0. If they are linearly independent though, the Wronskian is not going to give you 0. So let's look at e to the t and e to the 2t and show that they are linearly independent. Well, I can find the Wronskian. This is e to the t. Differentiate that, I get e to the t. Here I have e to the 2t. Differentiate that, I get 2e to the 2t. Multiply across here. So I'm going to take this times this and subtract that times that. And so this is going to be 2e to the 3t minus e to the 3t equals, well, e to the 3t. Now that is not 0 for all t. So that means these guys are linearly independent. And as long as it's not zero, I know it's linear independent. Why? Because linear algebra, that's why. So here I can find the Wronskian of guys, and I can determine whether or not they're linearly independent. And what that means as far as solutions to differential equations are concerned is that neither of these guys are redundant. E to the t and e to the 2t are not redundant in terms of their ability to solve a differential equation. However, e to the t and 5e to the t are. If you tell me one of these guys, it's the same as you telling me the other guy. Like, it's no new information. However, e to the t and e to the 2t, that's two pieces of new information. And that's the idea. This leads us to fact 4. If a fundamental set of solutions, and this is a very, very important fact, in fact, and a lot of things that we do in solving differential equations, there are times when I'm going to do things that is going to probably seem weird to some of you. That why are you allowed to do that? Why are you doing that? How do you know that that's going to work? Well, I know what we're going to be doing. I know it's going to work because of this little fact right here, right? If a fundamental set of solutions are found to an nth order linear ODE, I found n of them, n functions, and they're a fundamental set, meaning they're linearly independent, and each individually solve the differential equation. In other words, each of these guys, y1, y2, y3, all the way up to yn, they solve an nth order differential equation, and at the same time, the Wronskian of them is non-zero. Then an arbitrary linear combination of these solutions, C1y1 plus C2y2, is automatically a solution. I showed that by a fact earlier. And this combination forms the general solution to the ODE, meaning any possible solution that you can find, any solution that is out there in the entire universe or the entire multiverse, whatever you want to believe, any solution to this differential equation will be able to be written in that form. If you find an answer and it's actually an answer, it's possible for me to write it as a linear combination of y1 through yn. And if you find an answer and you can't write it in this form, it means it's actually not an answer. You made a mistake, right? So this is the general solution. If you can find n linearly independent functions that solve an nth order linear ODE, then it turns out that that is the general solution. A linear combination of those is the general solution. Every solution that could possibly exist for that ODE can be written in these forms. And on top of that, given any set of initial conditions for this differential equation, I would be able to find specifically what the C1, C2, C3, C, all the way up to Cn are that will not only solve the differential equation, but actually fit those initial conditions. And again, that's something that follows from linear algebra. And I'll talk about that as well. Okay, so we have a question here. What if we have n solutions and only 2 out of the many are redundant? Well, I'm not, let me say this, and I think this will answer your question, right? So let me say what I'm saying in another way, and I think this will make it clear to you. Suppose I have an nth order linear differential equation, right? It has n derivative, the highest derivative is the nth derivative. And let's say, for example, it's 3. I have a third order, just for argument's sake. It means that I should be able to find 3 linearly independent solutions. Meaning, if I find 3 functions that solve it and 2 of them are redundant, it means that I need to find a third. There's a third one out there that I haven't found and I need to look further, right? So if I have 3 solutions to a third order differential equation, and then I check the Wronskian and it's 0, and I find that, oh, 2 of these guys are redundant. So those guys collapse into one solution. They're really only one solution. So what it really means is I effectively have 2 solutions. And it also means that there's a third one that I'm missing. I'm definitely missing something, okay? On top of this, I want you to be able to understand that once I find those three solutions whose Wronskian is not 0 and solve the third order ODE, then there is no fourth type of solution. There is no solution that is linear. There's no fourth solution that is linearly independent to all the previous three and at the same time solves a differential equation. Such a guy does not exist. There will be three distinct solutions to a third order linear differential equation. There has to be three. If you only found two, or you found a bunch and they're all redundant, and when you collapse all of them, you get less than three, it means you're missing solutions. There are guys out there that you haven't found. On top of that, once you have found three, you do not need to look for any more. That's all there is. That's all that could ever exist. So now, if you go back to what we looked at in the last class and look at these solutions that I wrote down in light of what I just said, I'm looking at a second order linear differential equation here, which means it should have two solutions, which means I should be able to express it in this form: C1 times the first solution plus C2 times the second solution. And there is no C3 times the third solution. That is, if I put in a C3, it's automatically redundant. If it's actually a solution, it's going to be redundant. There are only going to be two for a second order ODE. And so when I got a repeated root in one situation and I only found one solution, I knew that was not enough. So what did we do? Well, we went and we invented reduction of order. And reduction of order helped us find what the other solution is going to look like. And then I can come back and fill in this table. Okay, that's what that solution has to look like. Because I cannot have only one. It's a second order. I have to have two, specifically two. Right? There has to be two linearly independent solutions to a second order linear. There has to be exactly three linearly independent solutions to a third order. There has to be exactly four linearly independent solutions to a fourth order, and etc. So once I know that one guy is missing, then I need to go through some method to find the others. I need to get n solutions for an nth order linear differential equation such that all these solutions have a non-zero Wronskian, meaning that none of them are going to be redundant, right? And so this is why I can say, if we're doing a second order linear differential equation, the solution has to look like C1y1 plus C2y2. There has to be two pieces. There has to be a linear combination of two distinct functions where one of them is not a constant times the other, right? I must be able to do that. And here's the thing. Because that is what the solution has to look like, and I know how many of them there should be, here's the thing that's going to be kind of weird, here's where the weirdness of differential equations comes in, which it bothers some people who don't understand what's going on. So I'm going to explain to you guys what's going on so that you're not going to be confused when I actually start doing all these weird things. Because an nth order differential equation has n linearly independent solutions, then it turns out that if I can find n solutions, it does not matter how I find them. Once I can find n functions that are linearly independent that solve it, I have found all solutions. This means I can be in a situation where I'm going to do some random hocus pocus and get a solution, and you can't knock it because, hey, I just found another guy that's linearly independent. Whatever I did to get that guy is not going to matter. As long as I end up with n solutions that are linearly independent to this nth order, that is all that matters. It doesn't matter if I randomly guessed what a solution was, or, you know, I rolled a dice and figured out what a solution was, or I used my children's birthday and combined that with the fourth digit of pi, and then, you know, did whatever to find the third solution to a third order linear. It does not matter what I do. Whatever I do to be able to find n solutions to an nth order differential equation, they're all linearly independent. That is good enough. So there are going to be times, it doesn't matter if you use magic. It does not matter what you do. So there are going to be times when we're moving forward where I'm going to say, hey, let's just pretend a solution looks like this. Or let's pretend we can find a solution that behaves this way. And then I'm going to work it out and I'm going to get that solution to work. And I'm going to say, all right, that's the general solution. And you're going to be like, well, how can you do that? You can't just randomly guess and make something up and hope it works out. And then if it works out, you say that was the answer all along. How can you do that? Well, linear algebra is why I can do that. I can do that because linear algebra guarantees that I only have a certain number of solutions, and that number and those solutions, if they're linearly independent, it can be uniquely expressed in this form. So no matter what method I use to get to my hand on those guys, it's fine mathematically speaking. Of course, you're going to want to be able to do this in a way that's repeatable. You don't want to randomly use magic, even though technically you could. You want to be able to find ways of getting solutions such that you can teach it to someone else and they can repeatably get solutions, and the process can be repeated, right? So technically, magic is a valid way to do it if you can find the solution, but also it's not the preferred way to do it because you do want to be able to have your methods repeatable so that different people can find solutions to differential equations whenever they need to. So in some sense, a lot of the things that we're going to be doing is going to be random, and we're going to do some guesswork, and we're going to have a lot of hope that maybe a solution can work out that looks like this. But at the end of the day, we're going to do this in a way that is repeatable, that I can give you a strategy for how I'm guessing solutions, and you will be able to guess solutions and find it too. And don't worry, if you find n solutions that look different from mine, they actually aren't different. We can both rewrite our solutions in the form C1y1 plus comma, all the way up to Cnyn. All our solutions, even a million different people find n solutions to an nth order, and they all look different. It turns out they can all be written in the same form. There are only really n solutions. And so no matter what method you use, as long as it's repeatable, we don't care. Just get to n solutions for an nth order, linear, and we are fine. And a part of that comes from linear algebra, because that matrix is guaranteed to have a solution and to have a unique solution if by Cramer's rule. So I know exactly how many solutions there needs to be. So find a way to get me that number of solutions and we're golden. As long as it's repeatable, we are fine. And so moving forward, just keep that in mind. There are going to be times where I'm going to be randomly guessing stuff, or I'm going to say, hey, let's hope that a solution could do like this. And you're going to be like, Jhevon, this is math. It's not about hope. It's not about faith. It's not about guessing. We need to be able to figure this out. And on the contrary, that's not true at all. And why? How do I know? Linear algebra and the existence and uniqueness theorem is how I know. And by the way, in general, you'd be surprised. A lot of new math theory is developed by just guessing and hoping, but that's a discussion for another time. A lot of math is just done by, well, I don't know what to do, so let's try something and see if it works. And then you kind of, in hindsight, prove that something like that would always work. And that is the case for differential equations. All right, so let's review one of our examples with our newfound knowledge. Let's look at this guy. Now, this was an example that we did last class, but now I'm going to redo it. And now we're going to look at it from the perspective that I introduced today. So first of all, I would notice this is a solde. This means second order. This means there are two fundamental solutions, right? So just by me looking at this, I don't even know what the solutions are right now, but I know there are two of them. In fact, I also know the general form of the solution. The general solution is of the form y equals c1y1 plus c2y2, right? So just by me looking at this equation, I automatically know all of that as a fact. That's just a fact, right? By linear algebra and the existence and uniqueness theorem, that is a fact. The solution to this guy is going to look like this. So now the question is, well, how would I find such a solution? So now comes the guessing. I'm going to say, well, all the coefficients are constants, so in order for the derivatives to cancel each other out and give me 0, I'm thinking that the derivatives have to all be similar to each other. Do I know a function where all the derivatives are similar? Yeah, the exponential. So right here, now I just go in and I guess, a pure hopeful guess, a hopeful guess. The solutions look like y equals e to the RT. And it's just a hope. That's all it is. The first function that comes to mind that I think could do something like what I need it to do is the exponential function. And you know what? I can guess. And it's fine. Because if I get this to work out, then it's actually going to be the solution. Once I can find two guys, it doesn't matter how. So here, this leads to the characteristic equation. So this leads to the characteristic equation, and that leads to the first line in my solution. I'm going to realize that this is going to look like r squared minus 4r plus 3 equals 0. And I showed this in the last class, so I'm not going to redo that again. But me doing this guess leads to this equation. And then I want to find the solutions to that equation. So here my r, this is going to be like a minus 3 and a minus 1. So here I get r equals 3 and r equals 1. And so this means y equals e to the 3t is a solution. And y2 equals e to the 1t is a solution. I just found two solutions to a second order linear ODE with a hopeful guess. And you know what? It is completely fine. This means that the general solution is going to be C1y1 plus C2y2, which is C1 e to the 3t plus C2 e to the t. And that coincides with the information that I gave you in the table last class. That coincides with this scenario right here. So I told you that this would be the answer, but I never really explained why. And to some extent, I still haven't fully explained why, but now you can see when I decide to solve an equation like this in this form, what is happening is that I knew this was the case. And I knew that whatever I could do to get my hands on two solutions, it was the case. So I just made a hopeful guess that would make my life easy. And hey, look, it turns out that I could actually get it to work out. So yes, it was hopeful and I just lucked out that that worked out. But you know what? This is something that works and it is repeatable. I can get a million different people to solve this second order differential equation in this way, and we'll all get to the answer. So yeah. That leads us to how we would solve a second order linear homogeneous differential equation. Okay. So hopefully that sheds some light on why I can do certain things I can do. But now there's some more that I want to explore about the Wronskian. Okay. Now, finding determinants, I know it might look like I just did something that's super convenient and anyone can do this and whatever, but if you have any experience with linear algebra, you're going to know that finding determinants can be difficult. The bigger your matrix is, the harder it is to find a determinant. And even for like a computer doing this, finding determinants is going to be very difficult in general if you start getting big enough. And this is true with just numbers in the matrix. So imagine it can be a lot more difficult when we have functions in the matrix. So finding determinants is something that is how we do it. That's how we can find the exact, the Wronskian of a bunch of solutions, and I can figure out that they're a fundamental set of solutions. However, doing this in general for n functions, it's really computationally intensive. And so we kind of want another way to get to this, right? So suppose, and I'm going to show you now how we can get to that. So suppose I have this second order linear differential equation. It's homogeneous, it's right here. P and Q are continuous functions on some open interval, and y1 and y2 are fundamental set of solutions on that interval, meaning the Wronskian of y1 and y2 is non-zero, they are not redundant, and the general solution to this looks like C1 y1 plus C2 y2, right? All of that we know in the background. Now, here's what I'm going to ask you guys to do. Consider what the Wronskian and the derivative of the Wronskian would look like, and use this to determine the form of the Wronskian. It turns out I'm going to be able to determine the form of the Wronskian without actually doing a determinant. Let's actually look at what that would look like. So I know what the Wronskian looks like. It's y1, y1 prime, y2, y2 prime. That's y1, y2 prime minus y2, y1 prime. Okay, now if I find the derivative of this, then of course I would use the product rule. So I'm going to find the derivative of y1, leave the derivative of y2, plus leave y1, find the derivative of y2 prime, which is y2 double prime, minus differentiate the y2, leave the y1 prime, minus leave the y2, differentiate the y1 prime to get y1 double prime. And do any of these guys combine? So here, you'll notice that these guys here cancel out. And so the derivative of the Wronskian looks like this expression right here. y1, y2 double prime minus y2, y1 double prime. Okay. Now, how can I use that to my advantage? So here's something cool. And once it works out, you're going to be like, wow, that actually worked out. Okay, so here's what we're going to do. Now, look at this one. Since y1 and y2 are solutions to the equation 1, this means if I plug in y1 and y2, it solves the differential equation. So y1 double prime plus p y1 prime plus qy1 should give me 0. And on top of that, if I plug in y2 double prime plus py2 prime plus qy2, I should also get 0. That is just by knowing that they are solutions. These two guys are solutions of the ODE. And so here's what I'm going to do. I'm going to take this, call this equation 1, call this equation 2. I'm going to actually rewrite these guys. So I'm going to take equation 1, and I'm going to multiply it by minus y2. So I just took the first equation and I multiplied by minus y2. Why'd you do that, Jhevon? Hold on. Then the second equation, I'm actually going to multiply by positive y1. So I took the second equation, multiplied by y1. Now what you'll notice is that the last term on the left side, qy1, y2, is actually the same in both equations. I can now eliminate. So if I call this equation 3, let's say, and I call this equation 4, let's say, then I can take 3 plus 4, add these two equations, and what would I get? I would get y1, y2 double prime minus y2, y1 double prime. I would get also plus P times y1, y2 prime minus y2, y1 prime. And these guys would actually cancel each other out. And then I would get 0. Now, anyone notice anything? What is this guy right here? And what is this guy right here? What's this one? Right, that's W prime and W respectively. So, undo. This here is actually W prime. I derived that for you earlier. This here is W. Those are the guys right here, W prime and W. So in other words, this gives me an equation, W prime plus P times W equals 0. So I now have an equation with the Wronskian involved and a derivative of the Wronskian involved. Look at that. I just created a differential equation for the Wronskian. What kind of a differential equation is this? How would you solve this? It's linear, yes, first order, yes, but if you were to solve this, it is first order linear and you could use the integrating factor method, but you're thinking too hard. There's something that you should see first. It is first order linear, but yes, Roberto got it. It is also first order separable. I can separate the equations, separate the variables. So this is dw dt is equal to minus pw. And in other words, dw over w is going to be minus p dt. I can integrate both sides. So now I get ln of w is equal to, well, p is a function, so I don't really know what the integral is going to be, but it's going to be minus the integral of p of t dt, whatever that is. And then I can solve for w, and I would get a constant times e to the minus integral of p. So it turns out that I can actually find the Wronskian of a second order ODE by doing that formula. Instead of doing a determinant, I can actually figure it out what it is up to a multiplicative constant. The C, I would need more information to be able to find it, of course, but at least I can tell you what form it's going to be in. And I can kind of judge on that, based on that, what the Wronskian is going to look like. Is it going to be non-zero? Is it going to be 0, etc.? Now, here's the thing. This leads to this guy here. So this is just a copy from your class text. This is a generalization. This is not in your textbook, but it's a generalization. So this leads to the following fact. If y1 and y2 are solutions to this differential equation, and the Wronskian is this, then the Wronskian is given by a constant times the exponential of minus the integral of p. So you look at the coefficient of the y prime, integrate that, take the negative of it, put that in an exponential, multiply that result by a constant, and that is what your Wronskian is going to look like. This was discovered by the Norwegian mathematician Abel, and it's called Abel's theorem. A lot of people call it Abel's identity or Abel's formula or Abel's differential equation. I believe Abel's formula is probably the most common way to refer to it, but your textbook calls it Abel's theorem. And this allows us to find the form of the Wronskian. This actually generalizes to higher orders as well. So yes, this is what it would look like for a second order, but you can actually kind of do a very similar thing with linear algebra for much larger systems and figure out what it would look like for nth order. And this is what it would look like. So it's still going to be some constant. So this here is still some constant. and it's exponential of e to the minus integral of p n minus 1. And what is that? Well, it's still the coefficient of the n minus first derivative. So you want to know what a Wronskian is going to look like for a second order? Just take c times e to the minus integral of the coefficient of the y prime. What about a third order? It's c times e to the integral of minus the coefficient of the y double prime. What about a fifth order? The Wronskian is going to look like c times e to the minus integral of the coefficient of the fourth prime, right? And you can actually do this in general, and that's what it would look like. Now, I believe your textbook has some homework problems that deal with that, but I don't believe this was actually stated. So I just copied that from somewhere else. But that's Abel's formula. You definitely need to know this version. And the course supervisor loves asking questions about this particular kind of thing, where he asks you about the Wronskian, how do you know a Wronskian would exist, and blah, blah, blah. So now, here's the thing. This also gives us the power to talk about finding solutions to linear ODEs. Because as long as your constant is not 0, then the Wronskian is never going to be 0, which means we're guaranteed to be able to find a solution to this, right? And the only time you can't find a solution is if the C is always 0. And then what that would mean is that the Wronskian is always 0, and the solutions, you can't find a fundamental set of solutions. However, we'll discuss this in the existence and uniqueness theorem, that for an nth order linear differential equation, we will always actually be able to find a fundamental set. And we'll always be able to find something such there's a non-zero constant here, which we'll talk about in a little bit. So let's use Abel's formula to find the Wronskian up to a multiplicative constant of this guy. And I'm going to verify my answer using the straight up determinant, okay? And that's how we're gonna end this section. So here, by Abel's formula, the Wronskian is going to have this form. C e to minus the integral of 3 dt. So the Wronskian should look like e to the minus 3t times some constant. Boom, Abel's theorem tells me what the Wronskian is going to look like in 2 seconds, right? Now, of course, I don't know exactly what it is because I don't know what the C is. However, I do know what it's going to behave like, right? I know it's going to behave like some constant times e to the minus 3t, which gives me a lot of information. So I can know that as long as my C is non-zero, this guy's going to have a fundamental set of solutions, and I can do a whole bunch of things with it, right? Let's do it the long way. So first, for the long way, I need to find the homogeneous solutions. So I have y double prime minus 3y prime plus 2y equals 0. Now I'm going to have to find the solutions and then throw them in that determinant. And of course, we remember what this means. So this is just a recap from last class. I will have this characteristic equation, this guy factors. So I'd have r equals 2 or r equals 1. This means that my y1 is e to the 2t, and my y2 is e to the t. Actually, this was a positive because just noticed that I wasn't getting an answer I expected, and it's because I messed up and I forgot that there was a minus 3 in here. So this is actually a plus e to the positive 3t. Okay, now that's going to make sense. So now, if I were to find the Wronskian, that is going to be e to the 2t, 2e to the 2t, e to the t, e to the t. And I can take this times, I can take this times this, minus that times that. And so here I can get e to the 3t minus 2e to the 3t, which is minus 1 e to the 3t. And look at that. You compare this. Going to compare it to that. And you'll see that I knew in a very short span of time what the Wronskian was going to look like. It's going to be some constant times e to the 3t. And then after actually finding the homogeneous solution, which by the way can be difficult in general, then finding a whole determinant, then I end up with the information that it's some constant times e to the 3t. And this can be a very difficult process in general. We have a very easy differential equation to deal with here. So here you can notice that Abel's theorem gives you the Wronskian a lot quicker. Instead of finding the homogeneous solutions by some painstaking method and then finding some huge determinant, I can do a single integral, and that is equivalent to this. Now, you would remember that we actually found the Wronskian of these two guys earlier. I did them in the other order, and I got a positive one here, but that just goes to show you that the constant here can be arbitrary depending on your perspective. It can be plus or minus, but one of the most important things is that it's non-zero if we want a fundamental set of solutions. And that is the Wronskian. So that is Abel's theorem. Very important. This you definitely need to know. So the course supervisor, the guy who's writing your finals, he loves asking conceptual problems about this kind of problem type. Is there a shortcut for finding a Wronskian? Or how do we know that a solution can have a unique solution, a differential equation will have a unique solution? And then one way, an easy way to answer that is to just, we can find the Wronskian by this integral, it's an exponential, it's not going to be zero, blah, blah, blah. And so you can answer a lot of things by Abel's theorem. So it's a very important theorem. In the past, on written exams, I've actually seen it required that a student actually go through the proof of Abel's theorem. And so I used to tell my students, just memorize this proof right here. It's more or less straightforward, so it shouldn't be too hard. However, for you guys, you're gonna have a multiple choice thing, so you're not going to have to know how to write out the proof, but you do need to know the statement. You need to know, I can find a Wronskian up to a multiplicative constant by this formula, if I'm looking at a second order linear differential equation. And that is it. That deals with some very important facts about the solutions to ODEs, which that is going to inform a lot of our decisions moving forward about what the solutions to a random ODE would look like. So yeah, I expected to get to variation of parameters today, but it doesn't seem like it's going to happen. In the few minutes we have remaining, I'm going to actually talk about non-homogeneous solutions to soldes. And then we're going to wrap up there, and we can pick up with variation of parameters tomorrow. So in this section, I want to look at a more generalized version of the equation we were looking at. For the last two classes, we always assumed that the right side was 0. Now I want to talk about the case where the right side is not identically 0. G is a function that's in general. It might hit 0 at certain points, but it's not always 0, right? The existence and uniqueness theorem guarantees that the above has a unique solution on I. So what would the solution actually look like? What I want to do is start with the higher order version. I'm going to show you what the solution here would look like, and then you can actually break it down to the second order version. So here's the thing. Suppose I have an nth order linear differential equation. All these functions are continuous on some open interval I, and so I'm just only there. Suppose yp is some particular solution, right? Now, there's various ways how you can get to this solution, but let's pretend that we could find a particular solution. There's one solution out there that's a specific guy that I can find. Tomorrow's class and the class after, I'm going to give you methods for finding this solution. But assume we can find a solution, and assume that y of t is the general solution, which was guaranteed by what I mentioned earlier. So it's going to be something that looks like c1y1 blah, blah, blah. Then consider what happens if I look at the difference of these two. Take the general solution minus the particular solution and plug it into this equation. Notice what's going to happen. I would be able to get y minus yp to the nth derivative plus pn minus 1, y minus yp to the n minus 1th derivative, n minus 1st derivative, plus dot, 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 plus p naught times y minus yp. I can group these guys based on the y's and the yp's. So the derivatives distribute. So this would look like y to the n plus p to the n minus 1, y to the n minus 1, plus dot, 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 p naught y, plus yp, or minus yp to the nth derivative plus pn minus 1 yp to the n minus 1st derivative plus p naught yp. There. Now this guy here, this is equal to g of t. How do I know it's g of t? Because I assume my y was a general solution to this equation, which means if I plug y in here, it gives me g as a result. Since y is the general solution. Also, this guy here is also going to be g, since yp is a particular solution. Since yp is a particular solution. So it's one specific solution that I could get my hands on. But it is a solution, which means if I plug it into this equation, if I plug it in on the left side, g should appear on the right side. And so, of course, what you're going to have here is g minus g. And so, ultimately, this whole thing gives you 0. In other words, y minus yp is a homogeneous solution. It is the solution that gives you a 0 on the right side. Right? So y minus yp is a solution to the homogeneous equation. This is when you have a 0 on the right side, which means y minus yp is equal to y sub h, which I introduced earlier as the notation. Or in other words, y is equal to y sub h plus y sub p. In other words, here's how, if I don't have a homogeneous differential equation, how things are going to look. The general solution to a non-homogeneous differential equation has the form y sub h plus y sub p. Your y sub h is the homogeneous solution, which I already talked about how you guys would find it. So that guy has the form c1y1 plus c2y2 plus dot 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 cn yn. And then y plus yp, which is a very specific solution that you could find for the non-homogeneous version. And so this is what a general solution is going to look like. And that leads us to this summary right here. That's the main takeaway. If you have a general nth degree, nth order linear differential equation that's non-homogeneous, the general solution has this form. Or if I spread it out, it has this form. So I know that if I can find n a fundamental set of solutions to the homogeneous version, plus some specific solution to the non-homogeneous version, if I add them, I get the general solution to this ODE here. What does this look like for second order differential equations, linear, that are not homogeneous? Well, again, your general solution is YH plus YP. And if you spread that out, this is what it's going to look like. C1Y1 plus C2Y2 plus YP. That's what it will look like for a second order non-homogeneous. So I explained here why we could make the guesses that why would you even think of saying, oh, let YP be some particular solution and look at the difference. And again, I don't really know for sure, but it's actually very similar to something that you would see in linear algebra. So for those of you who know linear algebra and you have a linear system, if it's a dependent linear system, the solution always looks like something like this. There's going to be some specific vector that solves the system. And then you're going to have C1 times one vector plus C2 times some other vector, where each of these vectors solve the homogeneous version of the system. And so that's something that happens in linear algebra. And so because we use a lot of linear algebra in differential equations, someone just randomly guessed, hey, maybe something like this is going to work out. And hey, because of the existence of uniqueness theorem and what I mentioned earlier, it's fine. Whatever way you can get to the solution, I don't care, as long as it's repeatable and it allows us to find n different solutions for an nth order linear differential equation. It does not matter. So it turns out this method is how we can solve a non-homogeneous differential equation. I do want you to notice that it includes the solution to the homogeneous differential equation, which is why we still needed to go through figuring out how to solve it if there was a zero on the right side. So now if there's not a zero on the right side, this is how you would solve the differential equation. And so we know how to find the C1Y1 and the C2Y2. So now the question is, well, how would I get a hand on YP? How can I find a particular solution? There are three main methods: variation of parameters, undetermined coefficients, and the annihilator method. We are not going to cover the annihilator method because it's really equivalent to the undetermined coefficients method. We generally only cover variation of parameters and undetermined coefficients in this class. And so that's what we're going to cover next time. Variation of parameters and undetermined coefficients. These are two methods for finding the particular solution. So tomorrow, we're going to start out by talking about variation of parameters, and it's going to be a lot more linear algebra. It's this guy here, which I guess I can put the notes in the PDF to today's class, so you can read through it and maybe work through it yourself, fill in the blanks, and see what you can figure out. And then we'll actually pick up with some examples next time. So for now, we will stop there, which is, yes, a lot of theory, but it's important for you to understand how we're going to build up solutions moving forward. So tomorrow we'll get down to more specific examples. But for now, we'll end right there. A lot of talking and all that, but hopefully you weren't too bored to death by that. It's very important. Throughout the semester, there are probably going to only be like one, maybe two more lectures where it's going to be like that, just me like doing a lot of talking and actually lecturing at you the whole time, not doing a lot of examples, but it's going to be some important things for you to understand. So this was the first of a very long theoretical lecture, but it does hopefully give you some insight into when you actually do want to solve an equation, what do you need to look for? How many things do you need to find? And how do you combine them to say, oh, here's the general solution? What we spoke about today goes a long way in helping you understand that. And tomorrow, I'm going to show you how you would find a particular solution, that YP guy. So for now, we'll end there. And that's it. I'll drop the PDF in the link to the video, and you guys can actually work through the variation of parameters, but we'll go through it as well tomorrow. So tomorrow, variation of parameters, maybe I can cover undetermined coefficients in the same lecture. And then on Thursday, maybe we'll do an application. We'll see. But your test will cover, you will be responsible. Remember, your test is on Friday. I'll give you an entire day in between. So your test is going to cover everything I cover up to tomorrow. So whatever I get up to tomorrow, that's what you have to know for the test. Whatever I teach on Thursday, I'll probably put some bonus points on the test regarding that stuff, but you're not going to specifically need to know it. So that's that. So thank you guys for joining. Stay safe. We're already a few minutes over, so let's end it right here and not draw things out anymore. And I will see you guys in the next one.